Okay, the purpose of this video is to look at one proportion, two proportions, confidence interval, and hypothesis testing, looking at the OpenIntro textbook and using RStudio to do our computations. First, panic, time to panic. Parameter, identify the parameter of interest. True proportion. Assumptions, what are the assumptions? Independence, success failure condition, check those. Name, what statistical procedure are we using? Name it. Interval, let's compute the confidence interval. Conclusion, let's give a conclusion. Let's say that we are 95% confident that the true proportion, in the context of course, lies between these two values, and maybe what that means as a result. So let's go right ahead with our work on this. In the book, this section 6.1, inference for single proportion, 6.2, difference of two proportions. We'll be using the formulas, we'll be using functions from RStudio, and we'll go right with a first example. Okay, here we go. First example I want to look at is the one on top here for one proportion, OpenIntro. 421 out of 826 randomly chosen borrowers support a new regulation requiring lenders to pull credit report. Okay, this is from OpenIntro 6.5. 421 out of 826. Let's compute the confidence interval. So this is really done immediately in RStudio in this way. 421, 826, 421 success, 826 is trials, and we'll put a 0.5 here for the value we're going to be, the proportion we're going to be assuming is the null proportion, and there we have it. Okay. Notice it says we have a one sample proportion test with continuity correction. The data is 421 out of 826. The null probability is 0.5. The 0.5 we put in the list of three numbers was the null value. Okay. The 95% confidence interval is computed for us. The sample estimate is given for us as well. Okay. Now there is some additional things we can tell in our test. So for instance, we're going to say correct equals F, and then we get a slightly different result. It says without continuity correction. Now one sample proportion test without continuity corrections. Okay, this is a technical thing. We typically want to have correct equals F. Okay, the values change a tiny bit. Okay, now confidence interval is computed for us. To 0.4756278 to 0.5. If I want to just look at it directly, I'll put the result of my prop.test into res, and then I type res conf.int, and it comes up in this way. Okay. Now let's go ahead with our values. X we said was 421, n we said 826. Our estimate, I want to go with the formula now. It's x over n, and with an alpha level, if confidence is 0.95, then alpha is 0.05, and with the critical value from the normal distribution, we have to check that. Of course, we have the randomness, and we also have a random sample, and we also have success failure verified. Of course, we have more than 10 with 421 and 405. So we have more than 10 in both cases, so we can pull from the normal distribution. Okay, and what we're putting from normal distribution, 1 minus alpha over 2, and the standard error is computed using the square root of x over n times 1 minus x over n divided by n, and the lower limit then is computed just as the estimate minus the z critical times the standard error. The upper limit is computed as the estimate plus the z critical times the standard error, and a confidence interval then is putting together the lower limit and the upper limit. And if we look at our CI, this is what we have. If we just go ahead with rounding our CI to 3 decimal places, and if we also round the result of prop.test confidence interval to 3 decimal places, notice we get the exact same result in this case after rounding. Okay. You should know there's another formula for computing confidence that was called binom.test, and so we could do the same thing. Say we have 421, we have 826, and I want to compare with 0.5, and here's the results come up. Notice, and you can compare with what we just found in terms of confidence interval. Very close. This time, this is using the binomial distribution. Okay. So let's look at another example. 39 of 250 randomly chosen patients are observed to have asthma, and one wants to test the hypothesis that the probability of a random patient having asthma is 0.15. Okay. So they're randomly chosen, so randomness is there, independence is assumed. Okay. We're going to be looking first at the parameter. Which parameter? The true proportion. Right? The probability of a random patient having asthma is 0.15. Well, true probability, true proportion in this case, essentially equivalent for what we're asking. The assumption, we have randomness, and we have success failure, 39 successes, and the others is more than 10, of course. Success failure is checked. So we go ahead with a test, hypothesis test for one proportion, and we're going to go ahead and do a computation. We'll get a confidence interval, and we'll be able to conclude. So 39 of 215. Okay, so prop.test, and this is 39, and it's 215, and we could put 0.15 in here, and we've got enter here. Okay, and we had one sample proportion. Let's just first check here. What's 39 out of 215 is 0.18. Okay, so so let's do it again with the continuity correction being set up to false. Okay, and this is what we have here. Alright, so we have all our results. Confidence interval is computed. Okay, if we're to use the confidence interval for our test, then we'd see that 15% is in the confidence interval. However, if we are really after this hypothesis testing, and the p-value shown here is too high. Okay. And the p-value shown here is too high at the confidence level, 95% confidence level. And so the p-value that we have is 0.1973. Okay, if we again save this in the result, we have res.p-value, there it is, 0.1973 is too high, and we don't have evidence against the null, so we fail to reject the null. Okay, but the null probability is 0.15, and the alternate would be that it's not 0.15. Okay. So p-value being high means we fail to reject the null, meaning the null holds. Okay, so yes, that's right, 15% is to be accepted in this case. Okay, next we look at an example for two proportions. This is from OpenIntro 6.11. In a randomized experiment for patients who underwent CPR, in the control group 11 survived, 39 died. In the treatment group 14 survived, 26 died. Is the difference statistically significant? So using RStudio, I'm going to have the x is 1426. I have that y is 1139, and I just want to make a table so this can be presented in a good way. It's x, y. Notice what m looks like now. There's dim names that we can call on. It's x, y, and a, b. Let's just change that. So dim names of m, I'm going to change that. It's going to be a list, and I want the experiment to be equal to the first part. I would like its treatment and control, and the second part is outcome, and that one is survived versus died. So now if I type M, it looks certainly nicer. So in the treatment, 14 survived, 26 died. the control 11 survived, 39 died. And so now if I do prop.test with M, I want to not give anything else. It gives me an answer, and notice it assumes a 95% confidence interval. So let's do the same thing, but let's do it at 90% confidence. So how do we change that? Okay. So first of all, we want the correct to be false, and then we want the confidence level to be 0.90. When we do this, we get a result, right? Proportion 1, this is for, if you recall, 1 is for our treatment. We have 35%, and for proportion 2 we have 22%, and the confidence interval is between. So let's put the result here in a variable called res, and res, the confidence interval is this. We can of course round this if we'd like to say 3 decimal places, and now we got negative 0.027 to 0.287, exactly as you'll find it for example 6.11 in the book. So for the next example, in 747 of Rocky Mountain spotted fever from the western United States, 210 patients died. Out of 661 cases from the eastern United States, 122 died. So here we have two different groups, okay, western versus eastern, and then we have two possible outcomes, survived versus died, and so we want to compare the proportions between the groups. Yeah? So this is about two proportions, and we want the true proportion in both cases, and we want the difference. And so do we have, we're going to assume there's independence, that the cases were selected randomly. We have no evidence here, but we're going to assume that. We clearly have in each case the success failure condition is satisfied, and then we'll move forward and we'll do a computation, confidence interval, and hypothesis test. Okay, is there difference statistically significant? So to work this out in RStudio, prop.test is going to do the work for us. So 210 died, 122 died. So let me have this C 210, 122, and we have total, and the totals was 747 and 661. 747, 661, and for prop.test we can just immediately give died, total, we want the correct to be false, and the confidence level, we just, if we don't put anything, it assumes 95%. So we go right ahead and we do our work here, and it's all given to us. So notice the two sample test is died out of total. The p-value is really low. Yeah? So this is 5 zeros before the first 2 comes up, so 0.00002. So it's very small. It's evidence against the null. And the null will be that the proportions are the same, and so the alternate hypothesis, the proportions are not the same. 95% confidence interval is from 0.05 to 0.14. Notice 0 is not in there. Right? So this is what you can expect. If you have very low p-values, you have evidence against the null, the difference is not 0. Right? And so 0 shouldn't be in the confidence interval as well. The proportions are computed for the sample estimates, for proportion 1, for proportion 2. And so here we're able to really make a conclusion that there is a significant difference, statistically significant difference at 95% level confidence, that the proportions are not the same. We can provide a confidence interval, we can provide a p-value, and we can go for further conclusion in comparing the Western versus the Eastern. And so this concludes our way to use RStudio for one proportion and two proportion tests.